Hi again, everyone. We are back and we are going to talk about another big point when it comes to calculus and especially limits, which is going to be continuity. So there's going to be a couple different aspects of continuity we're going to talk about, especially regarding limits. Um, but I think they're all pretty straightforward, so it shouldn't be too bad of a day today. All right, so first let's get the formal definition of what it means to be continuous at a point. So while we may have thought of the word continuous as maybe slightly different before we got to calculus, now we have a more calculus-based definition. So we need these three definitions, three requirements to be satisfied in order to be continuous at a point. First of all, the point must be defined, which feels pretty obvious. There must be a point in order to be continuous at a point. The limit at that point has to exist. And in fact, the limit at that point has to be the point that we have. So if we do not have any of these three things being satisfied, then we are discontinuous. Essentially, the most important thing is really just this third aspect right here, because one and two is taken into account in three right there. So the limit as x approaches a of f of x must be f at that point a. If that's true, then we are continuous at that specific point. Now, that doesn't mean that the function is necessarily continuous. That just means the point is continuous. All right. Now we can go ahead and check to see if a function is continuous. So I want to note that this is not looking at the limit of the function. This is just seeing if we have a continuous function. So we do have a slight difference between continuity and limit. So remember, a function can have a limit where it is not continuous, where there is no point, but a function cannot be continuous if there's no point. So for example, if I had a function that kind of went like this, had a hole, and then went on, the function has a limit here, but the function is not continuous here. So that's just kind of important to make sure that we understand the difference. So this says using the definition, determine whether the function f of x equals x squared minus 4 over x minus 2 is continuous at x equals 2. So we'll look at x squared minus 4 over x minus 2. Now, some of you may be inclined to look at this and say, hey, look, x squared minus 4, that factors. How nice. We could factor it, we could cancel it. And if you do that, it may look like it's continuous. But we're actually going to define something a little bit later on today that shows that this is actually not true. So what we'll do is all we need to do is try to plug in the number. If the number plugs in and it works, then we're good. If it plugs in and it doesn't work, which essentially just means that we're dividing by 0, then we're not good. So we'll plug in 2. When we plug in 2, we get 2 squared minus 4 over 2 minus 2, which is 0 over 0, which is not good. Therefore, this function f of x is not continuous, specifically at x equals 2. In fact, it'll be continuous everywhere, not x equals 2, but it's specifically not continuous at 2. And we know this also because what is x equals 2? Well, if it's in our denominator, then x equals 2 is a vertical asymptote. I'll put this as like a little note. I don't know why it doesn't write down there. Sorry, guys. Note, x equals 2 is a vertical asymptote. And the definition of a vertical asymptote is quite literally that it's not continuous there, that we cannot have a function that goes through that vertical line. So if we have a vertical asymptote and we're looking at that, just kind of consider that that's not going to be a function, continuous for that specific function. All right, now we can look at piecewise functions. So these are maybe a little bit more fun to play with because we're looking at two different functions kind of stuck together with different domains. And we're trying to see if this is continuous given the requirements that we have kind of imposed on this piecewise function. So using the definition again, determine whether this is continuous at 3. So in order for it to be continuous, now we do really have to consider what the definition actually is. But instead of really looking at the limit here, all we need to consider, let's call this maybe function 1 and function 2, is that the points that we get when we plug in 3 in function 1 and function 2 are going to be the same. So we need f of 3 for, I don't know exactly how I want to denote this. Let's go for function 1 to be equal to f of 3 at function 2. All right, so let's go ahead and check that. So for function 1, f at 3 equals negative 3 squared. And this is really important. If you have the negative and you have the squared, the 3 just goes in, or whatever you have just goes in right where your x is. So the negative just does stay out front. So that's plus 4, which is negative 9 plus 4, which is negative 5. For your second function, we'll say f of 3 is 4 times 3 minus 8. 4 times 3 is 12 minus 8, which is going to be 4. 4 is not negative 5. Therefore, f of x is not continuous. Specifically at x equals 3. And in fact, it won't be continuous. No, it will be continuous everywhere, actually. It just won't be continuous at the specific point. So we'll have kind of a jump looking function here, and we will define this as a jump discontinuity in a second. All right, and this last one, we have sine of x over x and 1. This is another piecewise function, except that we have a function that kind of encompasses everything except for x equals 0. And then we're saying at x equals 0, we are putting in a specific point. So this is really the only time when we may have something in the denominator where we don't have a value that may exist, and then we put in a value there. That's the only time where we may have the possibility of being continuous. So if you recall from one of the very early on lectures, we actually looked at this at a table of values to determine what the limit as x approached 0 of the sine of x over x was. And we looked at it from the left and from the right, and we made a table. And we actually determined, if you look back or you look at a table of values or you create the table of values, that this limit of the sine of x over x was equal to 1. And again, you can confirm this. So if we know the limit as x equals 0 of this function is 1, then we actually can use the formal definition to confirm this one specific case. So the formal definition said that f at a exists, that the limit as x approaches a of f of x exists, and that in fact the limit as x approaches a of f of x is f at a. Okay, so we have the first part. So this is like 1, 2, 3. We have, let's see, this is number 2. We have that number 2 works, right? And then this gives us 3 as well. This gives us what the limit actually will be. And we need to check to see if it is f of a. So f of a is at the point a. Do we have a y value? At 0, we do have a y value. It's 1. So f at 0 is 1. So this is like the first quantity here. Sorry that it's out of order. And so 3 says, is this true? So is the limit as x approaches 0 of the sine of x over x equal to f of a, which is 1? It is. Therefore, this function is continuous. So f of x is continuous at x equals 0. And in fact, we're continuous everywhere, because the only point where we weren't continuous, where sine of x over x was discontinuous, if you will, was at 0. So if we're continuous at the one point where there could have been an issue, then we're continuous everywhere. So, and in fact, f of x is continuous everywhere. So that's just kind of an extra little note. It wasn't asked in the question, but it's just a nice little thing to consider. All right, here's a little theorem. I think that most of you could probably assume this. It says that polynomials, first we'll just maybe consider the polynomial part. They're continuous everywhere, right? So if you have some sort of a polynomial that goes on like this, obviously that's going to be continuous everywhere. You're never going to have any opportunity even to have an open circle. Now, rational functions, you may. So rational function, again, remember, is that polynomial over a polynomial. That is your function. So rational functions are continuous everywhere in their domain. And so maybe you have a function that has a vertical asymptote or it has a hole in it. So those obviously just wouldn't be part of the domain. So therefore, everywhere that is in the domain will be continuous. So let's look at some examples. So for what values of x is f of x equals x plus 1 over x minus 5 continuous? So the first thing we would typically want to do is see if there's any way we can factor and cancel any values. X minus 1 and x minus 5 are the simplest that it can be already. We can't simplify them because they're already linear functions by themselves. So what we have to consider, since they're already simple, is where is this function discontinuous? Well, x plus 1, the numerator, is continuous everywhere, so we don't necessarily care about that. What we do care about is the denominator, because we know the denominator cannot be equal to 0. So we know x minus 5 cannot be 0, which means that x cannot be positive 5. So the only condition on this function is that x can't be 5. So what values of x will be continuous? Well, everywhere that's not, x equals 5. In interval notation, we may write negative infinity, comma 5, use a parenthesis to indicate that we're not including it, union 5, comma infinity. So this is the domain of continuity. You could also just say everywhere that's not 5. That's also an acceptable answer here. All right, now we can actually classify discontinuities. So there are 3 different types of discontinuities that we will want to consider. I will be referring to the actual names of these, so it is important to understand the names and what they mean. So first of all, a removable discontinuity occurs when we have, I'll try to write this. I don't think that this actually says. Oh, I did write it down here. A removable discontinuity occurs when you cancel out terms from a rational function. So I'll put a little star here, star here. So anytime you have a function that is a polynomial over a polynomial, kind of like what I mentioned earlier, if we could cancel out terms, then we would have a removable discontinuity. What that would look like in the graph would actually just be a hole. So if you were drawing this function, you would just draw a little hole at whatever point you removed, you canceled out from your function. The next one is a jump discontinuity. So for a jump discontinuity, the left-hand limit and the right-hand limit exist, but the limits are not equal. This occurs mostly, you'll see this in piecewise functions. I'm so sorry, that's really ugly. I'll rewrite that. It's a common joke typically when I'm teaching, especially in person. My handwriting's really bad. My students will sometimes make fun of me for it. So it occurs in piecewise functions. So that's when you'll see, so this here, I'll do a little drawing for B. Maybe it'll come up like this, and then you'll have a little something like this going off like that. This is a jump discontinuity, and I think the name is pretty intuitive because you're jumping from one point to the next. Again, removable discontinuity is also pretty intuitive because you are removing a term when you're canceling it out. So removable discontinuity. The last one, again, also very intuitive. Infinite discontinuity is going to be when you're looking at a vertical asymptote. So you have some sort of infinity here. Alrighty, so either positive or negative infinity going from the left or from the right. You're also going to have that when you're looking at the limit going to a point. It will have an infinite discontinuity at that point, even if they're going to the same infinity, because you're not going to have any specific point at that spot. So you can see something like this, where they both go to the same point, and there's our vertical asymptote. I'll abbreviate it VA. Or you can see something like maybe one goes down, one goes up, and again, there's a vertical asymptote. or vice versa, where you could flip those two. So there's never ever going to be a point there. That's just the idea of an infinite discontinuity. It goes to infinity. All right, and there's ways that we can also determine that. So here are some visualizations of what I drew, just slightly better because I'm really bad at drawing. So remove with discontinuity, again, when you remove the term, you put an open circle here. You may not necessarily have a closed circle somewhere. That's something that typically you would put in or someone would put in and say, I'm just going to impose this point right here. That's not ever going to be actually part of a function though. So that's a removable discontinuity. This is the jump discontinuity. Again, this will happen with piecewise functions. You're never really going to see a function that would jump like that, unless it's two different functions with different domains kind of stuck together. And then this is your infinite discontinuity. Like I said, this will be a vertical asymptote here. Okay, now we can go ahead and try to classify some of these discontinuities. So we're looking at the same function that we had earlier. We already know that it's discontinuous at 2, right? But we can now classify that discontinuity at 2. So what we'll do is we'll first say to ourselves, well, what can we do with this function? Is there anything that we can do with this function? And the answer is yes, x squared minus 4. Some of you may recognize that as a difference of perfect squares. I'll put this as a little note. So this happens when you have x squared minus, I'll call it b squared, where b is any number. The difference of perfect squares is x minus b, x plus b. So if you ever see anything of this form, x squared minus some number squared, 4 is 2 squared here, then you can immediately write this as a difference of perfect squares, x minus, in this case 2, x plus 2. So we will say x squared minus 4 over x minus 2 is x minus 2, x plus 2 over x minus 2. You could also, if you don't remember that trick, you could just put in that there are 0 x's here, minus 4, and then you could use the typical method that we would have of two numbers that multiply to -4, but then add to 0, which would be -2 and +2, which gives you the same exact answer. So this is just kind of two ways of doing the same thing. All right, and when you look at this, what you notice is you have an x minus 2 here, an x minus 2 here, and when you cancel those out, this implies, let me redraw that one. This implies a removable discontinuity. And that's specifically at whatever the point is that you took out. So this is x equals 2. All right, so we don't care what the limit will be. You could compute the limit if you really wanted to. You'd see at 2, as x goes to 2, your limit's going to be 4. I'm not asking you to compute the limit here. I'm just asking you to classify a discontinuity. Here it's going to be removable because we literally removed the term. All right, here we see a piecewise function. So with a piecewise function, you can have kind of any of them. Most likely you're going to have a jump discontinuity, but we just want to kind of confirm that. This, again, is the same function that we had earlier, and we're trying to classify it. So what we determined earlier is we said this is function 1, maybe this is function 2. For function 1, f at 3 we said was -3 squared plus 4, which was -5, and at function 2, f at 3 was 4 times 5. Oh, sorry, that's 4 times 3. I don't know why I keep doing that. It was 4 times 3 minus 8, which was 4. Obviously, these two things are not equal, but because the point is at 3 for both of them, we are jumping from one point to the next. So this is a jump discontinuity. So if you remove a term, it's a removable discontinuity. Honestly, in a piecewise, most likely, if it's not continuous, it's just going to be a jump discontinuity. And let's take a look at the last case. So we're looking at x plus 2 over x plus 1. We again want to see what's going on. You're not going to have jump given a rational function ever. So we're just really considering if it's removable or infinite. This is pretty easy as well because x plus 2 over x plus 1, there's absolutely no way of simplifying this. You can't remove anything from it. So that tells us at x equals minus 1, there is a vertical asymptote. And at vertical asymptotes, that is an infinite discontinuity, which is an infinite discontinuity. So I think, again, these aren't too bad. Just classifications, pretty straightforward. All right, now we're just kind of going to shift gears a little bit. There's a theorem that says trig functions are continuous over their entire domains, which I think we probably could have said knowing what the trig functions are. And the key here is the entire domain part. So some of you could think of, say, a tangent function, which goes like this, and it goes like this, and it goes on forever, and you have like a vertical asymptote in between each one. And some of you may say, well, that's not continuous everywhere. And you'd be correct if the word was everywhere. But the key here is their entire domains, and their domains just consist of the spots in between the vertical asymptotes. And they are, in fact, continuous from vertical asymptote to vertical asymptote. So trig functions are continuous over their entire domains, which means that if you're looking to take the limit of any type of a trig function, all you have to do is plug in that value, ideally. Unless we have an example like the video before where we have, say, sine of 1 over x. Maybe we'll use the squeeze theorem. But for something as simple as this, we can just plug in whatever value it is, and it should work. So we see as x goes to pi over 2, we'll just go ahead and plug in the value to compute the limit. So this is the cosine of pi over 2 minus pi over 2, which is the cosine of 0. And this is a little throwback to making sure that we remember our trig values. So in terms of trig, what you really need to know is this first quadrant. If you know the first quadrant, you know all 4 quadrants. There's special values. At 0, that's just this right here. All right, and the really important part about this is going to be the coordinates. So this is 1, 0, because this is a unit circle. At some point, I will go a little bit more in depth going through all of the values because there's 3 special values here, here, and here. There's going to be a value here. There's special values around the entire unit circle that we have. I will go into those a little bit further, but these are something that you should know, and it's something you could also very easily Google if you're looking at like a homework assignment or just trying to learn the material. And something that's important is that your x value is the cosine function and the y value is the sine function. All right, so if you're looking at the cosine of 0, 0 is the angle measure. This is 0. Cosine is x. So your answer is just whatever x is. X is 1. So your answer is just 1 here. All right. If you're looking at this and you're having a little bit of a hard time kind of recalling trig, that's okay. A lot of people probably are. I do suggest you either come talk to me, and we can do a little bit of trig review, or you find I can give you some resources, or you find some resources online, and definitely do a little bit of review of trig, because trig will definitely come back up, honestly, sooner rather than later. All right. Now we have another theorem. So we talked about the squeeze theorem. This is another pretty important theorem. I'm giving us another, like an alternate version. This is the one that the textbook has. This is one for the continuous case. So this is called the intermediate value theorem. This says if f is continuous over a closed bounded interval, so f has to be continuous over a closed bounded interval. Z is any real number between f of a and f of b. Remember, so f of a and f of b are going to be your y values. Then there is a number c in a to b such that f of c equals z. So we're just saying in between 2 y values, if it's continuous, there's a value in between those 2 values. All right. There is an extension to this theorem that I wrote here, which is if f of a and f of b have different signs, so one is positive and one is negative, and it's continuous, then there exists a c such that f of c is 0. So then we have a 0. So essentially, if you have a function like this, where this is a and this is b, then this is f of a and this is f of b. Therefore, there exists at least one C, call that C, where f of C equals 0. So these are both different versions of the intermediate value theorem. You could be asked to use the intermediate value theorem to show that there's a 0 in an interval, that there's a number in an interval. Again, so similar to the squeeze theorem, it's not like the most important theorem. We're not going to use it a whole lot, but it is important to know. So this is just a little depiction of the first part, right? If you have some A, some B, you have some number, C or Z in this case, in between them, satisfying f of C equals Z, like this. So any of these numbers would satisfy that. Alrighty, let's do an example. So this says show that f of x equals x minus cosine of x has at least one zero. So they haven't given you an interval. They have not given you a closed bounded interval. They've only given you a function. So it's kind of up to us to create a closed bounded interval, knowing that x is continuous and cosine of x is continuous. So that means that f of x is continuous. So we need to create a closed and bounded interval and find that this will have a 0. And so we're going to use my version of the intermediate value theorem that says if we could find one f of whatever it is we plug in that's negative and one that's positive, then between them, naturally, it has to cross through the x-axis, which is the definition of a 0. All right. So you may have to plug in several numbers before you actually get some that work. Now, of course, I know which numbers are going to work because I made the lesson. But you may have to plug in several to be able to find some where you get a negative and you get a positive. So this is, again, really going to be where your knowledge of trig will come in. So I'll draw a little unit circle. All right, so again, cosine are your x values. So we need a cosine where if you do sum x minus cosine of x, you get positive and you get negative. My first suggestion is try 0. 0 is a pretty easy number to work with. 0 is right here. The coordinate on this unit circle is 1, 0. So f at 0 is 0 minus cosine of 0, which is negative. Cosine of 0 is 1, negative 1. So now we know f of 0 is negative 1. If we need to show that this function has at least 1, 0, we now need to find some x value that has a positive y value. And if we can do that, we know at some point it has to go through the x-axis, just naturally. Well, this is where we want to try a few things. I'm going to go ahead and just plug in the next easiest number to choose, which is going to be the next axis. So this is the point 0, 1. And again, remembering that cosine is x and sine is y, this angle value is pi over 2, or 90 degrees, if you will. So f at pi over 2, and in calculus, so in pre-calc, you may have used degrees and radians if you took pre-calc. In high school, you also probably used degrees a little more than radians. In calculus, we will not be using degrees. You can use degrees and convert back to radians, but we will pretty much exclusively just be using radians. So we see f of pi over 2 equals pi over 2 minus cosine of pi over 2. Well, cosine of pi over 2, that's the x value. When your angle is pi over 2, the x value is just 0. So you have pi over 2 minus 0 is just pi over 2. Well, pi, we know pi, that's 3.14 divided by 2. That's a positive number. This whole thing is positive. So we found between 0 and pi over 2, we have a negative number and a positive number. So on the closed and bounded interval from 0 to pi over 2, we have f at 0, negative, and f at pi over 2, positive. Therefore, there exists at least one 0 in this interval here, 0 to pi over 2. Now, that's not saying that we know where the 0 is. Actually, we're not saying we know where the 0 is. We're just saying that there is one. So this theorem, again, that's why we don't really use it quite so much, because it's not specific. It just says there's a 0, but how many? I don't know. There is one, though. So it's good to know. but we're not going to use it too far into the course. All right, this is an application. So it says if f of x is continuous over the interval from 0 to 2, f of 0 is positive, f of 2 is positive. Can we use the intermediate value theorem to conclude that f of x has no zeros between 0 and 2? Explain. So this is a really good application question to get you thinking. So what I might suggest is we do a little drawing. So 1, 2, and here's 0. We know that f of 0 is positive. So I'll just choose some number up here. I don't care which value. I'm not even going to assign it a value. I just know it's positive. So here's 0, and I know that f of 2 is also positive. So somewhere up here. And it's continuous. So that's the key. So this value here and this value here, they connect somehow. But we're not told a rule for assigning one value to the next. We have no clue how this thing actually works. We don't know how to connect 0 to 2. So can we use the intermediate value theorem to say that there's no intervals? Well, I don't know. Theoretically, we could have a function that just goes like that. Well, if that's the case, then right, we don't have any zeros. We could have a function that goes like that. Well, we wouldn't have any zeros. But we could have a function that goes like that. Or we could have a function that goes like that. In which case, we do still have f of 0 and f of 2 positive, but we have no clue what's going on between them. And so because we have absolutely no rule that tells us what's going on between them, the intermediate value theorem doesn't actually help us here. So can we conclude that it has no zeros? No, we don't have enough information. I'll try to write a bit neater. And this little drawing here is also good to show like any of these are valid functions, and we don't know any, if any, may work. But this is enough to say like we could have some zeros. All right, here's the last question for today. Show that f of x equals x cubed minus x squared minus 3x plus 1 has a 0 over the interval 0 to 1. So now we actually are given the structure that the intermediate value theorem kind of said from the beginning. We don't have to come up with an interval, they give us one. And we have a function. And this is a polynomial, therefore we know f of x is continuous. So my suggestion is if you're given an interval, use the endpoints. Let's go ahead and use both of the endpoints and hope that those things work. If not, then we can try some numbers in between them. But since we have square brackets, we know they're included. So if those two endpoints give us what we want, then this is a really easy problem. So we'll try f of 0. Well, if we plug in 0 for any of these x's, that just becomes 0. So this is just 1. What about f at 1? Well, that's 1 cubed minus 1 squared minus 3 times 1 plus 1, which is 1 minus 1 minus 3 plus 1. 1 minus 1, that just goes to 0. So that's negative 3 plus 1, which is negative 2. So we have f of 0 is positive 1, f of 1 is negative 2. Since 1 is positive and 1 is negative, we know that it does have to cross through the x-axis. So show that it has a 0. There we go. We've showed that it has a 0. So this has a 0 in 0 to 1. All right, that's all for today. If you have any questions, let me know, and I'll see you next time.